Okay, hi everyone. We are continuing our review of discrete computation for version 13. And we had looked previously at these lovely coloring functions. Where had we got to? We had been looking at planar graphs, right?
And Dominator trees.
Which we got a little bit stuck on.
Right, because the documentation wasn't fully updated.
Okay. Okay, and we want to understand whether Dominator tree and that whole lingo is the best and right lingo for that. Is that the only name that those things are known under?
The only one.
Yes, that's kind of, at least as far as I know, and I looked actually. So it's...
Okay. So let me understand. So this is Dominator. So this is like a transitive reduction graph. I mean, it's the same general type of idea. I mean, not doing the same thing, but it's the same. Okay, directed graph from the root vertex V, Dominator tree. What is the relationship between this and a spanning tree? Okay, please don't do it this way. Please, when you're going to do this, just put the frigging graph in here. Don't say G equals.
Yes, that's the first round of the, we don't do that. That's the first round of the example. We will fix that.
Okay.
We will fix that.
Okay. And what's this plot theme name labeled? I mean, no, whatever. Why doesn't it? Okay, so, and this isn't even looking like a tree. Okay, so this is showing basically, given node 1, it shows everything that is reachable as a tree from that node. Is that correct?
Yes, but the parent is usually the unique path to that child, per se.
What if there isn't a unique path? What if it's a multi-graph?
But then there is no, the immediate denominator is just the parent above, like you see an example. So if it's not unit, it's the parent above. So it kind of will come back to the main root, per se.
Yeah, I mean, I think it's a property. Like if you look at the details above, right, it says, I think it's a property of what it means to be a dominator, right? That there is a unique path.
Exactly.
Okay. And is that the useful thing? I mean, what is the usefulness here?
Well, is that the dominator tree? I mean, it's applying, when people do compiler and other stuff. So it's kind of the usual constructor when you look at that.
Sorry, say that again. I mean, so I've got some random graph. I mean, let me make a random graph here.
Look at the applications. There should be applications.
Oh, well, I can't guarantee that we work on the application yet. So.
Extinction of species in trophic models. Natural loop detection. When it said a host, I was confused and thinking about server computation.
By the way, I mean, if it always does return a tree, is there also a dominator tree function which returns a tree object instead of a graph object? Or should there be?
Seems interesting.
Why?
Because we have a whole system for dealing with trees. But maybe you just say graph tree. You say graph tree of dominator tree graph of whatever.
I mean, you certainly could. But I mean, if the function always returns a tree and we have a special way of representing trees, then it might be worth.
Well, the question is, what do people want to use it?
No. We have special ways of representing trees within the graph framework.
No, that's not the point. The point is, what are people going to use this for? What is the workflow around a dominator tree graph?
I think we need to do applications then. This is one of these things. We can even pull it now if we don't feel it's not sort of mature. I want to see applications. This is what determines that.
Because this is taking the same options it says as tree graph which is turning a tree into a graph.
No,
Okay,
tree
fine.
graph
Tree graph is
an old function in the graph framework. That's a graph.
But it also turns a tree into a graph, doesn't it?
Yes, we added it after tree was introduced. I mean, we have to fundamentally make a distinction between a tree and tree graph, right? Tree tends to more represent a tree, using nested expression like in the Wolfram language, where there is a general concept of tree, which is an abstract tree, which doesn't matter the representation from double linked list to the Wolfram language, right? So
Yeah.
graph just
no,
that's
I agree. I agree. A graph tree, so to speak. I'm getting a tree as represented in graphs has less data. For example, it doesn't have ordering at every node.
Right.
Right?
Yes.
Right, and that information doesn't really exist in this case, right? There is no ordering. You can't have multiple copies of the same vertex, etc., right?
Well, you mean in terms of name, yes.
Yeah. So right. Okay. So I guess there is a reason why this should be a graph.
Fine. Okay. So now, okay, what is immediate dominator list?
So immediate dominator list just essentially give the list of predecessor, right? So usually you can represent a tree. But you can represent a tree by just giving for a given vertex its predecessor, which is kind of the syntax we use for tree graph, right? So you give a list and then we map to the predecessor. So that's one way, or we can actually construct the full tree, which is what Dominator tree does.
Sorry, I'm confused here. What is the difference between in component? How does this list 1, 1, 2, 2, 2? What does that mean?
So that's the list of so if you do vertex list of that graph, right?
Yes.
And you just put this. So for the vertex at position 1, his predecessor will be 1. Vertex at position 2 will be predecessor will be 1, and so on. So is that a representation of a tree using the predecessor list?
But I don't understand this one here, number 5. Right? Or number 5. Why is number 5 dominated by vertex 2?
Like you asked earlier, why there is no unique path except from 2. So that's why it's dominated by 2 instead of 3 and 4. Because there is 2 paths getting to 5. At least, yeah, 2 paths getting to 5.
I see. So this is the unique, this is kind of the pivot point to get to the rest of the graph. That the point, I understand what this is now. That's the thing that you have to go through. That's the bottleneck, basically.
Yep.
Maybe we should use the term bottleneck somewhere in the description. Does that make sense?
Yeah, we can try.
I mean, that seems to be the intuitive thing that's going on, yes? Am I confused in some way?
No, it's kind of that, the vertex such that every path goes to it. So it depends on the type of application, right? So in some case, you actually see as a bottleneck is, if that guy is.
Sorry, I'm sorry. The application is it where is the bottleneck that gets you to 5? What is the immediate bottleneck before vertex 5? Correct?
Yes.
That's what this is. Where does the terminology? Are you sure there's no other field that has another terminology for this?
I can't guarantee that they cover all fields, but that's maybe some other area discover it and rename it differently. That's possible.
So okay, so it seems like the term dominator let's see. So what one is getting I mean, isn't there a better look, these are vertices, right?
Yes.
Dominator vertex list.
Yep, that will work.
That's the list of dominator vertices as opposed to just vertex list. So it would typically look like, well, let's just think about that. So there's vertex list is a list of the vertices, and dominator vertex list, that seems to me sensible. Okay.
Okay.
And now, okay. Why are we saying tree graph here as opposed to just dominator graph?
Or because we tend to, in earlier, find spamming tree, we kind of try to, include tree when the output is a tree, or have this tree structure.
Okay, fair enough. Except we don't want to call this dominator tree because it isn't a tree in our sense of tree.
Yes.
Okay. But we still have fine spanning tree, right?
Yes.
Which is not a tree in our current sense of tree, right?
Yes.
What is it? It's a graph in our current sense.
Yes.
Oh God, look at this horrifying thing. Whatever. I hate this. I really hate this. Oh, whatever. I mean, the natural name will be dominator tree, but for the fact that, okay, and there's a unique one, obviously, yes. There's a unique bottleneck of this kind. Okay. Well, all right, dominator tree graph is probably okay. Interesting functionality, actually, now that I understand what it is. What is a dominating set? Isn't that what this dominating vertex list is? What's the difference between that and a dominating set? Also, there seems to be a notion of post-dominators.
I think the dominator set was, I don't recall clearly on my mind, but yeah, I think it was related more in terms of adjacency of vertices than anything else.
Oh, there's a completely different thing, which is a dominating set. Yeah, it's a completely different thing.
I think it,
which is not a dominator. It's a dominating set, which is a completely different thing.
Yes, unrelated to independent vertex set and such.
Right. Okay, what about post-domination?
So it's the reverse. So,
yes.
That post is an after or post is in a meal?
Post is an after.
Okay.
It just means the things where everything has to go through that bottleneck on exit, as opposed to going through that bottleneck to get to a node.
Right. Is there actually a function that actually does that, like a graph reverse or something like that, where it just takes every directed edge and directs it the other way?
I think there is a reverse graph, right? Isn't there?
Yes.
Yep.
Okay.
So you're suggesting that the post dominator be found by doing reverse graph?
Maybe, yes. I guess. Yeah.
But we should check that that actually is correct, that works, and we should give an example so people can search for post dominating set. Post dominator.
Yes, it was in plan to do that. Yeah.
Okay, and there's no sense of saying comma after or something after the node. Saying GV, the vertex comma after. Also, what would happen if you want multiple vertices? By the way, this is not right. This, oh yes, yes it is. I'm sorry. This is, wait a minute. Starting from that node, right, okay, that's right. But could you not start from multiple root nodes? No, I guess not. This is a deterministic, basically right. This is a deterministic flow of control. By the way, for goodness sake, mention the term flowchart on this page. Oh, it does say that. Okay. I'm just surprised that there aren't things in, the land of Gantt charts and so on where people have talked about this type of thing. Roger, do you know about that?
I'm not sure. I don't recognize this name, but this is a building block on top of which you build a ton of other things in compiler analysis.
I know about compiler. I understand about the compiler analysis case. I'm asking about the case if you've got some project management flow.
Yeah,
and you're asking,
there's usually a critical path, is what you.
Right. What is the relationship between a critical path and a Dominator tree?
I don't know. I know what a critical path is, which probably everybody else here knows too. That is the one that will dominate the timeline.
Right. But this is clearly a related thing because everything has to go through that node. I think let's look this up, okay? These functions are okay. Maybe we can make them experimental if we're not sure about the relationship to like critical path stuff and so on. Make sense?
Right.
Okay, let's continue looking. Graph, we talked about making it from molecule and tree expressions. So do we have any options when they're being made from?
No, there cannot be any options to control conversion in that case. Then we need a separate function. If there's sort of detail control, it needs to be a new function.
Okay, well, so for a molecule, a double bond is just a single edge, right?
Right.
I think we talked about this last time a bit.
We did, yeah.
Yep. Okay, did we see an example of the data structure conversion?
No, I haven't yet built it.
Okay.
But pretty much it will similar if you open, for example, the binary tree. They usually have visualization.
Yeah. I think we'd already looked at this. I don't know why we're going back to this. We were on to the geometry section.
Yes.
Okay. Let's not confuse ourselves. Two graphs functions that somebody's asking on our live stream realize that leaves are submissive to the right kind of dominant tree. That might be a pun, or it might be a serious piece of whatever, I'm not sure. Ethan is commenting, but it's the wrong group of people to talk about that our XML importer should be updated to turn XML into trees.
I completely agree. And I think that's the killer use case for trees.
Right. Which group is dealing with that?
That would be the tree group.
Are you sure? Do they know that? Not the import-export group?
I don't know. I don't think anybody is particularly assigned to XML. I think that's one of those where we've had people work on it, and I don't know that there's
okay, well, fine. But I think it'd be fine for the tree people, so to speak. That sounds wrong, doesn't it?
Yeah, it does sound wrong. No, but that's a really good suggestion, and I think that's the killer driver application for trees.
Well, along with, look, I don't know whether we've got text structure, for example. I don't know whether text structure yet supports a genuine tree output. Who's project managing or taking notes here?
Brady's here. I was just looking at Shadi's import-export formats list, and XML seems to be assigned to John Foltz. But either way, I'll send this to the.
That's crazy.
Yeah,
I
there's no way.
I understand. I'm just reporting what I'm.
I think it's because Jason was the key developer. Jason Harris was the developer.
Oh, okay. So it probably just went up. Anyway, I'll send this to the.
Right, but I think the two issues are, text structure. Is there a way to get a tree out of this? There should be. And generally our abstract syntax tree stuff. And by the way, another person connected to this is Chris Cooley with his what's currently in the function repository, the code structure function repository entry.
Okay.
Right, which is the thing that takes C code, for example, and makes abstract syntax trees from it. It should be rather easy to turn this into a tree thing, and I think the tree developers should look at it.
Yeah, we need. Yeah, okay. Yes, I agree, but we need to scale it a little bit.
Which?
Effort. The tree effort. If that's one person doing all that, it's going to be slow.
Well, I think it's going to get specialized, but the first thing is just to see how it flows, how the XML and AST stuff flows into trees, then go from there. Okay. There was a comment here about control flow graphs. Back edges. Okay. Control flow graphs and I don't know. All this stuff about cyclomatic complexity and all these kinds of things that are to do with essentially flowchart type graphs. Yeah, I think that's sort of where we're going here. But okay, let's jump to this. Okay, solid region. Okay, let me pull up the documentation.
So that page you really want to open in prototype if you're using 12.3 for the.
I don't know whether this. Okay, there we go. Hopefully. Right. Okay. Magnificent. So we've been waiting a long time for this. So a solid region. What about just a single solid region? I don't understand.
Well,
I don't understand this.
Well, actually, in principle, if you disregard the first usage is just a convenient way. But essentially, you have to specify the Boolean operation, which is, intersection, difference, or union, followed by the list of regions where you apply that. So the first case there is just.
I don't understand. We've got region union. Why is that not just working on solid regions?
It is. It is working now. It's working all since we shipped.
Right, but so is the distinction here that basically this solid region is a way, it's a representation of regions as, intersections and unions and so on of other regions, as opposed to region union, region intersection, which takes, some meshes and produces a new mesh. Is that the distinction?
Yes.
Yes. Plus, actually, here, we assume here the objects are closed. So that means also the operation are regularized or closed operations. So if you make the difference of two objects, the result will be an actual solid closed object. Where if you do region difference of two objects, you don't have no guarantee that it's actually closed.
Sure. Okay. So the basic point so a solid region is an object. It's not an operation.
Smell a rat here. I'm sorry. I smell a rat. This is, you are basically saying region union doesn't quite do the right thing. So let's introduce a new function.
No. Region union does the right thing. Everything works perfectly. Solid region is just completely different.
Okay. So let's just understand that. So if I take a region union of a ball and a cuboid, for example, what the heck is that? What do you mean it's completely different? I mean, what the heck is that?
That is the output. It's, the union of a ball and a cuboid.
Yeah, and what's the difference in that and solid region of union, ball, cuboid?
In this case, they're exactly the same.
Will the solid region evaluate to Boolean region, or will their full forms be different?
So the solid region is a representation. It's different full form. It's a solid region object.
I'm sorry. You're doing the same thing you've done a bunch of times. You don't like the way that region union works. So you're introducing a whole new world of other things that work in a different way. Am I wrong?
That's not the correct way. So solid region the goal of solid region is to do computational solid geometry.
Mm-hmm.
Right.
And what's okay.
Right.
So we could call it the CSG region.
Exactly. Where our Boolean operations are general abstract mathematical operations, like we usually do, two general, where you can't actually do much, right? So if you want to really compare. Right. So here the goal is to introduce an object, right, with a specific goal, a specific handling, right? The same as you can always claim that Boolean region is just implicit region. I mean, there's no point to introduce implicit region because you can always represent it that way.
I completely don't understand why region union, a Boolean cuboid, does not return the same thing.
So
I just don't understand.
So that's automatic visualization as we do for graph and meshes, right? So we plan to do that down the road when all the framework is in place to be able to do that.
So look at full form of the solid region you just ran. Right.
It is just the game of auto visualization. So we just, we have that on plan for Boolean operation in general. It's a non-trivial process.
Right.
We're working on.
So this thing would visualize the same way, but I don't understand what is the difference between Boolean region and solid region of union.
So I think first of all, Boolean region can do more stuff, so it can deal with non-solids. But okay. I still don't necessarily see why that,
lame argument.
Why you couldn't just use Boolean region, and when the arguments happen to be solids, that you basically do what solid region does.
Okay, so the first goal of this function is to do constructive solid geometry. So that means the assumption is that all the object and whatever you are manipulating are solid object. So there is no lower dimension, right, in your operation, or what you actually call regularized. So one example, which is more obvious to look at, if you do the region difference of two objects, you have no guarantee that the resulting object is a solid object. Right? So that's one example where there is a difference.
That's quite magnificent that works. So if I take that thing and I say volume of that.
We haven't yet implemented all that. We are working on that.
Okay, but that will work at some point.
That will work.
For 13?
Yes, it should be.
Okay, magnificent. Okay, so I'm still completely confused. Okay, so if I do region, okay, so let's say that I do region difference. Of ball, cuboid, right? Okay, now I say graphics 3D of that.
Region. You could probably just say region of that.
Oh, how really confusing. Okay. So now I've got this kind of weird judicicized thing. Okay, which is lower tech than this beautiful thing here, right? But it's the same, but lower tech.
No, it's not the same. Visually, it's the same, right? Because there is, right now, we don't have a way to display open set. So where you have the code there of the cuboid, right? You don't have actually that face. It's on,
So, okay, you shouldn't run volume of %10 because, okay, here's the point, right? There are many different internal representations, or actually you can even see it in the full form. There are many different representations of regions, right? And which have totally different, stored in totally different ways, right? So Boolean region is one way of representing a region. And when you just run region on it, it basically is just discretizing it and making a visualization. So when you say something like volume, there's going to be a different implementation of volume for every different type of region, right? So there's going to be an implementation for Boolean region and for solid region and so on. But so solid region is just another backend representation of this. But I guess maybe one question would be, should functions like region union or region intersection, when the arguments are solid regions, should it just return a solid region object, or should it return a Boolean region?
What does it do now?
So,
well, it's returning a Boolean region right now.
No, so what, at least from my point of view, region difference and such are operations, right? So if you take mesh region and you operate on mesh region, region difference and and such, do the right operation and try to remain in that subsystem of meshes. So if you manipulate solid region, we try also to preserve and return you an output in that right subsystem we have.
But this didn't define a subsystem. This region difference just said I've got a ball and a cuboid. I want the region difference of them. Nowhere did I say mesh it or anything weird like that. That's just historical because you happened to implement that a few years ago.
No. I mean, if you take a ball and a cuboid, you make the difference. We don't have an object to represent it in the system beside Boolean region.
And besides solid region of difference, comma, whatever.
Right, we can also represent it as solid region. That's true, that's one way. So.
But maybe that's what
so I guess the
be.
question is, yeah, right. I mean, is there any reason?
No, but in this case, region union, yes, but region difference cannot be a solid region. That's the thing. Because that object is not closed. It's not a, because you make a difference, that means at the boundary, when you actually cut, you remove that cuboid, those points don't exist technically.
Hold on. This is an open sets question. Is that what you're saying?
Yeah. So, okay, actually, I mean, we haven't brought this up, Charles, but when we do the Boolean operations right now, we intended to eventually have an option that controls whether you do regular closed operations or not. And for right now, the only thing we do are regular closed operations.
Yes and no.
What do you mean?
We went down to that path. I mean, it makes the whole system complicated. Intuitively, in terms of usability, if somebody take two mesh and operate on mesh, he assumed that the result will be a mesh object. Right? We can make the whole system complicated by saying an option, regularized operation or non-regularized.
Okay, hold on. There's a much simpler case, which is just intervals, right? This notion of closed and open intervals, we don't have, I mean, what we're dealing with,
It's more than open closed. Regular closed operation means that you take the interior and then you take the closure. So that means if you have just a lower dimensional thing will be blown away completely. There's nothing left.
Okay, so what you're saying is, if I make an inequality, let's say that I'm asking a question, is a point inside this region, and I have a point on the boundary. Let's say, for example, here, right? I say, is the center of the cube 0, 0, 0 in the thing or not? Is that an example of a question that would matter where this issue would matter?
Well, yes, but it's not the quintessential example, because that only thing that matters in your case is open closed. It's not the regularity bit.
So what you're saying is, if I take the ball and how do I get the boundary of the ball in this constructed solid geometry thing? How would I get the what's that?
Boundary region.
So region boundary. Boundary region is the other one.
Okay.
Oh, for God's sake! How is anybody supposed to remember that? Region. Okay, that's right. It's operating on a region. Region boundary of a sphere. Right. That should be. Well, I take that. I get that. Lovely. Okay. And that has, if I say what's the volume of that, it will say 0. What? Why is it saying that?
Because it's not defined.
What does that mean?
Because its sphere is just the. Yeah.
It's the surface. There is no per se term of volume. Yes, we can return 0, but it's not defined.
Why is it not defined? It's defined and it's 0, isn't it?
Well, I mean, if you actually ran the integral, wouldn't it be? It would be 0, right?
I mean, it's the same like say volume of a point,
which is 0.
The surface area of a point is 0.2.
Yep.
Okay, we can switch that.
I think so. I mean, I don't know. You tell me, but I think. I mean, what would Adam say about that, for example? From the point of view of algebraic geometry and so on, the consistent thing to do is just say it's 0. I think. I mean, perhaps I'm wrong.
As far as I know, it's, those operation like region measure, those operations are defined on the object based on dimensionality of the object, right? So when you have an object in dimension 3, you can talk about volume, but when an object is on the lower dimension, that concept doesn't exist.
Well, but you can also, this, well,
yes,
two things. At first there's the question of the embedding space, maybe, but also this sphere is like
not the embedding space. The dimensionality of the object.
Right, but this sphere has, is it like topologically, yes, right? Or like it is a two-dimensional, it's like a two-dimensional manifold, right? But it is, quotes a three-dimensional object, right? In the sense that its points are a subset of, R3 or something.
Right.
Look, the issue is volume referring to the embedding space, or is it referring intrinsically to the object itself?
It's referring to the dimension of the object.
Okay, then I could give an argument for why it should say undefined.
But for sphere though, for point, I might agree, but I think sphere though, given that it does seem like it is a three-dimensional object because it is a subset of R3.
We went to that part of saying undefined because you have arc length, surface area, and all those, concepts which are defined on that dimension of the object than just on the full space. Otherwise, you will just say, well, somebody give you an object of 20 dimension, the volume is 0. Somebody give you an object of 0 dimension, a point, it's also 0. Right?
Yeah, all right, fair enough. Okay, I'm buying into this. Although it will be good to make sure we explain that. This represents the intrinsic thing, not the thing. That may be worthwhile at some point to have a wrapper here that says a ball, a thing embedded in three-dimensional space, as opposed to this object itself, because this object itself is a 2D manifold. Am I making sense? As opposed to a thing embedded in three-dimensional space. Right? I think there's a distinction between those things for our purposes.
Yes.
That makes sense?
Yes.
So we may need that distinction. We may need, something like, I don't know, space embedded. That's a bad name. But okay, let's go back to this question, right? So I'm completely not getting this. Completely not getting this. And I don't think it makes sense. All right, so let's go through this again. So to me, region union should give me the union of those regions. Why is it not doing that? Why do I have another thing here that does that?
They both do it. One auto visualizes, the other one doesn't.
That's not an adequate answer. That's simply not an adequate answer.
So the goal of solid region is to be able to do computational solid geometry. So essentially giving a set of closed object, ball, and whatever object, torus and such, we should be able to manipulate them and do Boolean operation, essentially the 3 fundamental Boolean operation, intersection, difference, and union, and also obtain back those objects. So there is the same as we have mesh, right? There is a subsystem, right? Where the whole thing is consistent. Because mesh essentially is a union of polygon. But we can also claim that we don't need to introduce mesh, right? Region union of polygon will also cover mesh. But we introduce that subsystem because you can actually live in it, do operations in a consistent way.
Okay.
So that's the same case.
But I want to know, what is region union supposed to return? Why is it not returning one of these CSG regions, basically? Why is it returning a Boolean region rather than a CSG region?
We can probably do that later on. We are introducing cylinder region on this release, right? Boolean region was introduced years ago when we were doing, when we introduced region union. And Boolean region is that general abstract representation, because the first argument of Boolean region, you can actually give any Boolean function. Right? So it's that general abstract Boolean operation, which is kind of too general, and actually there's no, in principle, hope that you can actually compute anything which out of Boolean region. So
what is the decision process? Is it if I'm trying to decide, hey, should I be using solid region or Boolean region? assuming that it is possible to use solid region, right? I mean, what is there a case where I could use solid region, but I'm actually going to prefer Boolean region?
No, actually, the goal is, if you want to do modeling, you want to build an object, you use solid region because you can easily take, like that illustration there, you can actually construct object, easily by using solid region, by using intersection and difference. Let's
really see if I can cut through all of this. Basically, you have two different representations for solid geometry. One of them is in terms of meshes, where you break everything down to what is it? Is it surface meshes, or is it tetrahedra or something? What is the mesh structure for a sphere? That sphere I got. What is the ball? I should say. What is the mesh structure for a ball?
So
we have two. Okay. So and it depends on your application. The simplest representation is what's called a boundary representation, and that's a boundary mesh that just represents the boundary surface. If you need the internal structure, like in finite element and other places, you need to have an internal mesh, in which case it's typically tetrahedralized or broken down into smaller subregions for which one can solve problems.
But at the end, those two objects are roughly speaking the same, but just different representation.
Actually, I mean, this is sort of it's too late to ask this question by many years, but is there a particular reason why, like, in the graph functions, there are a couple different underlying representations, but they're all hidden inside of graph, but in the region functions, they're all exposed? I mean, is it just that they're sufficiently different in the region functions that it's worth making them more visible?
Yeah. Because there's things that make sense for a mesh that makes no sense elsewhere. Like there's a natural graph structure for a mesh, and we even have something called mesh connectivity graph that gives you all that. Those things, those notions of edge and face and those things makes no sense for any other representation than a mesh representation.
Maybe Christophe is asking more about, like, for graph, you have sparse representation, double linked list and such. Is it what you're asking?
No.
Yeah, but I think Roger answered it. Answered it, which is basically that. Yeah, but yes, I mean,
basic point is, look, the continuum. We have the continuum, which is what's going on here. This is the thing that is, hook, line, and sinker continuum. Whereas as soon as we've meshed it, we're not continuum anymore. Is that a fair way to put it?
No, because that's intended to approximate the continuum. But
I understand that, but you just said mesh connectivity graph, all these kinds of things. They are admitting the fact that a mesh is not the continuum.
Exactly. And people talk about them. People talk about polygon as if they are real things, and polyhedra. And they do very low resolution ones. Do you know what I'm saying?
I know, but so hence my point that conceptually, the difference here is between thinking about space as in some kind of discrete approximation and thinking about it genuinely as the continuum, where we have a purely symbolic representation that is just the continuum representation.
And just to build on what Christopher asked about, sort of the design that I envision for this at the region level, not at the sub-region level, like mesh regions and stuff. At the region level, we can have many more representations, and the whole thing is built to support multi-representation. So for instance, we're gonna do nonlinear meshes effectively, which is sort of a representation that they have in CAD systems. They're called boundary reps and uses NURBS to represent the surfaces and so on. So that's an important type of representation. A little bit later in the future, we might get to something called subdivision regions, which are popular in the movie industry.
Yeah, I understand. Okay. Where you're doing adaptive meshing and things.
Yeah, we're doing adaptive meshing anyway, but subdivision region are basically defined as limits of a subdivision scheme.
Oh, okay. Okay, but so let's zoom out again for a second, okay? So in this case here, for whatever reason, this thing chose to use the mesh representation for this region.
Right? No. What happened?
No, that's just visualization, Steve.
Just visualization, and it's You have to
Okay,
discuss that
okay,
anyway.
fine. So in the future, we might have better visualization.
Yes.
It doesn't show
In
meshing.
fact, we didn't tell you this, but under the hood, it's effectively using ray tracing. That's why it's looking so damn good.
Right.
It's using GPU shaders on your system, and it's using ray tracing in the 3D case.
Okay, well, that's cool.
And we are going to reuse that framework to actually render this one correctly. That's,
Okay,
part of
so
the-
fine,
this
but I'm
is
coming back
just
to my
visualization. Visualization is not
Okay.
the same as geometry. It's very
Okay,
important
all right.
to geometry,
So I'm
but
just
not the
trying
same.
to understand. We could say, when you say region difference, the question is, this is one, is there an identity? Boolean region of this is equal to
Yes,
solid
it
region
should be.
of difference or whatever.
Well, I mean, comes
No.
into the slightly subtle thing that Charles kind of hinted to, which we haven't fully resolved.
Which is lower
No,
dimensional
it's-
subspace.
No, in this case, it's not even subtle. They are completely two different results. Region difference, you remove the point.
We haven't settled that, whether this one should do that or not.
Okay, this is about lower dimensional subspaces. Is that right?
Yes.
Okay,
Yes.
fine. Okay,
Mm,
so
well, no, I'm confused. This is a state operation. You remove the point. Yes, we can complement it by regularization, but it's clear that you remove the point.
okay, but Charles, the difference between these things. So what we're saying is, I mean, you see, this is what's interesting is,
Charles, you know
in the-
what we need? We need an almost equal operation.
No, look.
I
guys,
know, Stephen. I know.
Right, this is the continuum meets the discretum. so to
Right, but
speak.
that's what I'm kind of saying is that two different kinds of equals. Is it's like almost equal, whereas say a mathematician would say it's equal almost everywhere or something.
Well, but look. The point is, we crossed the bridge of saying 2, the precise 2, is
Yeah.
equal to 2, the approximate 2 here.
Right.
Okay. What you are claiming is that for regions, you don't want to do that, right? And it makes sense, right? So if I say here, 2 is less than 2 point. Okay, that's interesting.
Yeah.
That's an interesting claim. I'm going to save this file because I want to.
Wait, isn't that what you expect? If they're equal, then you expect that 2 is less than 2 points can be false, right?
Well, is that true that it is always the case that I don't know the calculus of this. I mean, with floating point numbers, it's not obvious what the
Well,
what the
but
calculus.
do 2 is greater than 2 points. Also going to say false because they're equal.
Okay, fair enough. Fair enough. So its logic is if they're equal, they've got to be strictly, they cannot be strictly less than.
Yeah.
Okay, fine. But so what we're doing here is what you're saying is that the CSG region difference is the symbolic thing that is like the 2 here in some sense. They're
both like the exact, actually.
All right. Okay. Fine. Well, I mean, we could do an analogy here with intervals, an interval intersection, and so on. Do we have an interval complement? If we did, we will be thrown right into this issue, right?
Yeah, we don't.
So actually, I mean, out of curiosity, because it might already be implemented, what happens if you say region equal of these two things?
Exactly. Well, I mean, right now, I think we're not fully implemented anyways, but what Charles is arguing for that should be false, which I don't think we're ready. We're going to have some more arguing to do there.
And is that because if you said region member,
No,
and then you gave it like
just-
0, 0, 0, it would give different answers or something like that?
Just open the documentation of region difference and read the definition. That will tell you what will be the output without regularization or anything. It's a set operation.
Yes.
Right? And it's the complement or something, right?
But here's the issue that we've been struggling with, because we think that the vast majority, like 99% of people, want regularized operation for solids. Because
what does regularized mean again?
It means you take the interior and then you take the closure of the result.
And if you look at the second example in the 3D case there, you have two mesh, right? The cuboid and the cone.
Mm-hmm.
We actually return you a mesh because it's here that we actually do that regularization. Otherwise, mathematically is not correct. You don't have that boundary.
Well, there's that too. Yes.
Right?
Yes.
What are you talking about? So you mean by not having the boundary, you mean if I take the region difference, and then I ask about a point on the cone, that point on the cone should not be present in the region difference. Is that correct?
Correct.
Yes, correct.
But now it will say it is.
Right. So in
because
this,
what? Because you're doing this regularization?
No, because I mean, at least the logic right now, at least for me, was that when you're in the mesh subsystem, you are dealing with mesh. You are to manipulate
meshes can only meshes are closed.
Exactly.
Polyhedra are closed. Polygons are closed. They can't deal with some faces missing.
I mean, maybe they could, like maybe you could have some way of marking basically mesh cells as saying this is an open mesh cell, but that might
right.
be
but closed, you mean closed in a different sense. I mean, a polyhedron that's closed, it's like, does it let water in? But that's not what you mean.
It's a closed set.
Yeah, it's a closed set.
It includes its boundary. Right.
Yeah.
So, I mean, this is a question with intervals. It's a question with these things. Does the thing include its boundary? Right. And so ball, for example, presumably includes its boundary.
Yes, it's documented. Yes.
Okay. Could I get a ball that has been skinned that doesn't include its boundary? If so, how would I do it? Could I do region difference of ball, sphere?
Well, no. I think there's two issues here, right? I mean, I think the point is like potentially, right? There could be a version of ball that when you ask these sorts of questions, it sort of behaves like an open ball, right? As opposed to a closed ball. But the issue is that, for example, if that function like region difference, if it's going to return a mesh region, that right now there's no way of representing, open faces as in an open set in a mesh region. And so it's sort of like, and this is the same with a couple other types of representations too. So it's sort of like, it's hard for these functions to be totally consistent about how they handle open and closed sets, because sometimes they're returning representations that can't represent open sets. That's kind of the point. Okay.
Yeah.
Okay. So the question is, could there be a skinned mesh, so to speak, that has had, aka open, but that's a confusing way. I mean, it's just a confusing thing. That is something which does not include its boundary.
We say yes, but is it needed in the system? That's the thing.
Yeah. But the other thing is that you need to be able to sort of add and remove everything. Every point, every edge, every face, everything.
Well, you're saying you could have a sphere which is mostly includes its boundary, but has one point, the pole, for example, the North Pole is not included, for example.
Right. And right now, Boolean region represent all that. Right.
What do you mean by represent? So in this case here, for example, could I ask, okay, do we have a function that answers the question, is this a closed set?
No.
But we could, couldn't we?
Yes.
Then that might be useful in understanding what's going on.
We have
so the thing is this, we're threading a fine line here between sort of complexity of representation, usefulness, and doability, kind of.
I know.
Okay.
That's welcome to our world.
Yeah. Well, yes.
Right. We just have to be careful on this one, because this is exactly the same type of issue as this, right? We could have made the decision that those two things are unequal. That would have been silly. I mean, okay. So again, this question of is it open or closed? Okay. So you're saying region difference does this thing that produces, this accurately represents whether this is open or closed. If I were to do this as solid region, what would I get here? So if I say the seemingly indistinguishably different operation, but bizarrely with different syntax.
No, solid region doesn't take a sphere. Solid region, all the region it manipulates are closed regions.
Yeah, it's solid all the way.
Right.
It needs to be a solid arguments enclosed.
You use cuboid instead of ball. I mean, if you just want to see the difference, you can just try, the difference between a ball and a cuboid, and the difference between, and use region member on 0, 0, 0, right?
Yep.
Right. And if you do that region member on the Boolean region, we see that it will tell you, 1, 0, 0 is not a point of that region. No, solid region doesn't yet work on that.
Why does it say false?
We are still implementing, so I cannot guarantee
okay,
the
fine.
result.
So it's just a bug or something.
But if you try Boolean region, right, out 18, you should out 18, you should probably take 1,00, and hopefully will tell you false.
Okay, so region member %18 000, right?
No, 100, right? So you're on the.
Oh, I see the pole. Yeah. Okay. Whereas, okay, but we have no representation of 1 minus epsilon.
No.
And just to, I mean, this is, oh gosh, welcome to the crazy world of the continuum.
I mean, it seems like this is sort of, I mean, the basic point is that there's some pure math, there's some pure math and sort of topology related usages where you care about this, but everywhere else you don't.
But also the point 99 is more a numerical computation issue, where the one we are talking about is more a topological issue, right?
No, I know.
Part of the complement or the...
I know. Okay, so let's zoom out for a second here. Okay, so the first issue is you have a particular representation of regions. This CSG representation is a nice, clean representation that perhaps makes some slightly different assumptions about regularization.
Well, it is, I mean, actually, now that I think about it, it is the clean regularized operations. And then we can actually, then we don't have to have this potential hack that I've been worried about for years for the region, the other region operations.
So walk me through that again. So
when we did the original design of Boolean operations, I had these two worries. That is that the 99% of people don't care about the subtleties that you've been asking about.
Mm-hmm.
Because what they want is exactly this. They want CSG operation. They want to create shapes, they want to, like clay, basically.
Right.
And the thing is that, but mathematically speaking, that's just plain wrong. That's not what Boolean operations do if you define them raw. So the way that what people figured out then in the CAD world that modeled this for engineering systems and other things is that you should do, the correct thing to do was to do what's called regular closed operations, which means that you take the interior of the result and then take the closure. That means if the result was lower dimensional, there is nothing left. And if the result, had some open, missing some faces or some surface pieces, that will be added in, that will be closed out and filled in.
Yep.
And that made for a pretty good model, but then they ran into trouble. Well, let me skip the trouble bit.
Okay, but anyway, so what is your bottom line?
But bottom line is that we have been vague about what we do, because we wanted to strict that up, but we knew it's going to take several rounds of development to be able to live up to that, to do both. To basically have some kind of option that specifies whether you do a regularized operation or not. Because we also wanted our Boolean operations to solve other key problems like surface-surface intersection in 3D or ray-surface intersection.
Yeah.
And I think that those are very key, and we don't want sort of 15 other functions that solve, here's a surface-surface function, surface-surface intersection function, here's a ray-surface intersection.
So look, bottom line, it seems to me that region right now, if region could get some specification of whether it thinks it's regularized or not, and then there's contagion about regularization through the operations, that something like that could work.
Can I add something? Roger, I don't know if you forget, but we discussed this, right? So if you open the page of region difference, for example,
right,
the way we decided to go was with subsystem, right? Where we said the region difference of two boundary mesh region give you the smallest boundary mesh region. So we do implicitly that regularization.
That's true.
Based on the
subsystem. So that was the, yes, that covers that up. Yes.
Right.
Okay. So hold on. So here's a suggestion. Okay. Mm-hmm. So basically the idea is the region itself carries the information about whether it is intending to be a regularized region.
No. No, that's in the Boolean operation. That
wait. I'm saying, let's imagine that was the case. Okay, let's imagine like closed and open intervals, which are not, putting that.
But we need to do that with ball. We need to do that with ball and all kinds of things, primitives.
Yes, we would need to do that. Yes, we would need to do it. Let's just walk through this for a second.
Okay.
Assume that there was an option that basically said whether it was regularized or not. And assume that regions knew that, whether they were intended to be regularized or not. Okay, then all these operations like region difference, etc. Well, okay, so the first question is, when you do a region difference on a ball and a cube, what should it do? Should it use constructed solid geometry, or should it use? And the answer is, it seems to me, that's an implementation detail. That's not something you should stick the user's nose into. As far as the user is concerned, what it can return, it could be this, it could be some slightly different representation, doesn't really matter. It's a symbolic representation that then allows you to compute from it. But it certainly shouldn't be the case. But then the decision about which of those it uses is largely automatic. And it might make a particular choice if it can tell that all regions involved are intended to be regularized. It might decide to do one thing rather than another.
Right.
Go ahead.
Right, and it's actually, roughly speaking, what we are doing now. All right, and it's what I was pointing in that page, that we kind of implicitly say it for mesh, boundary mesh, and mesh region, and you see that in all those pages we said for mesh and boundary mesh, this is the result, because we roughly say when you're in that subsystem for the type of mesh, we want the regularized operation. But when you deal with graphic primitive and such, right? We associate them close to algebra, right? A ball is x squared plus and such, right? So we preserve that structure where it's kind of a state theoretical thing, right? So that means if you do implicit region and the implicit representation of a ball, and then you use the actual symbol ball, we give you the same result.
But the implicit representation is x squared plus y squared plus z squared less than or equal to 1. Is that correct?
Yes. So if
I said less than 1, what would I get?
You have an open object, it's not a ball. So that means when you do those, even you do region difference on that, the resulting implicit region, you actually see that the inequality is preserved, the output is preserved. Right? We preserve the fact that it's open.
Okay, fine. But you're saying in the case of constructive solid geometry, you would not do that. Is that correct? So I did the same thing. If I took an implicit region and I said the CSG region of my ball created by a strict inequality in an implicit region, and I did the exact same operation, what would happen? Would this give 0? Would this give the null set, or what would it do?
So first is because solid region actually will restrict you that you cannot actually do that. So solid region just take some, the list is, is down there. It's a specific set of lists, so you cannot actually even express it in that context.
Okay, fine. So this is essentially if I were to think about this in terms of algebra, for example, this is like, you usually use elliptic functions, but in this particular case, it can be represented as a square root. This is sort of a special function of, this is a representation of a region as a special function of regions. Is that a fair way to characterize it?
I mean, it seems like it's just, for example, a function like region difference will try to the extent that it can to have its output in the same representation as its inputs. And some inputs are capable of representing whether they're open and closed and some aren't. So it's more just a question of, region difference just has to know for every type of input, or maybe or the user has to sort of know for every type of input, does this, given the output type that I'm probably going to get, given this input type, and by type I mean like the type of representation, is that output type going to be able to represent open sets? If yes, then I can expect that they'll be correct. If no, then right. Of course there isn't going to be any representation.
So I'm completely not buying into the fact that these are two different operations. I mean, I don't understand why. To me, this region difference thing at best is a method option that determines, we can perfectly well have a special purpose CSG function. There's nothing wrong with that. But in terms of what region difference does, it seems to me it should be able to return both of those.
No, that's fine. I mean, there is no, I have no position on that. I really, the point was more like, we're introducing solid region for a certain goal, is to do solid constructive geometry, like in CAD system and such, as you point out, right? So if later on when we propagate it in the system and it happened that, region difference, we need to generate Boolean region or solid region, that's, from a point of view of our framework, it doesn't matter. It's just a representation of the same geometric object, and the system should handle it. So region difference can return Boolean region, solid region, and even implicit region. We actually do that right now. So they are all the same. So we just pick the one which is more appropriate for the subsequent operations.
1 second, I need to deal with one other thing. Sorry, please go on. Yeah, say that again. I lost that. I got distracted by something. Could you say that again?
No, saying that, region different and subsequent function in the geometry framework can return Boolean region or solid region. That's fine. I mean, in the whole subsystem is built that way, right? And that was not, is not that representation which is actually this, the main goal here. Here, solid region, we push to introduce it because it allows us to do computer solid geometry, as well as represent all our, objects coming from CAD system and such. Right. So
right, but it should be transparent. I mean, in other words, if I say this name is just not making it, that it's not the general solid region.
No, it's not
general solid region. This is a specific representation, just like a boundary mesh representation or any of these other specific.
I think it should maybe be CSG region might be a better name, actually.
Just for the fun of it, when you say it's not really the solid region, what do you mean? I can prove that all solid region are equivalent to that, but that's
no, I realize that. But what I'm saying is, in our system, what I meant was that the generic way to represent a region is the region, is the region wrapper. And the region wrapper already knows it has multiple different internal representations, depending on whether it's an approximate mesh or whatever. So there are two different issues. One is, what is its internal representation, which in the case of graph, you have very successfully hidden that from the user, and the user doesn't care, right? In the case of
it's relative, because in terms of graph, we have pad graph, we have tree graph. It's just that when we went to the design, we decided, we should just abstract it and return one object.
Absolutely, graph. Right, which is great, and it works very well. Okay, so for regions, what we're saying is we can't quite do that.
Right.
Because and it's really because of the long claw of the continuum, basically. If we could do things purely symbolically, we could do that. If we wanted to do things purely symbolically, so that they are effectively represented discretely, then that will be fine. The difficulty is that in our non-continuous world, we cannot represent the continuum perfectly, except by virtue of unevaluated operations. So, okay, so what we've got is region is now approximated in various ways, but it still should be the case that, you could not know about any of that, and you could just use the region wrapper to represent a region, right?
Well, okay. at the level that there are operations that we call region operations, they should apply to every possible way that you can give a region. It's like region member really works on everything. Okay. The things that are named mesh, they work on mesh things. So mesh connectivity. These are things that apply to sort of that family of representation. Just as we have other special representations like polynomial, it's kind of general, but you know, and it's very useful. But it's not the same as a general function. Do you know what I'm saying? It's a special family of functions.
Right.
You know, and we have a whole slew of operations that work on polynomials. And we have kind of a family of operations that work on meshes.
Yes, I understand. And you can convert a region to a mesh.
Right.
And that's fine. But I'm saying that region difference better just eat, you know, any implicit region or whatever. And
it does.
Okay. So here, basically
solid
what you're saying,
or CSG region is more restrictive in that it takes other CSG region as input, or it takes these base primitives. And an original CSG was just
so let's not call it solid regions, because that's what's confusing me.
I agree.
If it says CSG region,
okay,
we're all
so
good.
Every meeting we've had now for half a year, I started by saying I really don't like the name.
Okay. Well, do we want to call it CSG, or do we want to call it constructed? I think CSG is what everybody calls it. And
that's what I think too.
And it's somewhat technical, and you have to understand what's going on to use it, basically.
Yeah. I think it's a good name. I've gotten used to it by now, so it's like, oh yeah, this probably should be CSG.
I mean, although that's probably right, but I mean, but also, like, I don't know, if there's someone who's not super technical, but is like, I'm trying to design this part for 3D printing or something like that, they probably do want this, but they probably will be scared away by CSG.
I think they would know what CSG was. But they also won't want this. They won't use this. They'll use region difference on these things, and it will return a CSG region. They'll never see it because it will auto format, and they'll just be happy.
Right. You know, that's the ideal case, I guess. Yeah.
Right. I mean, the fact is that the only thing we're doing here is to reveal the fact that it is a CSG region instead of a Boolean region, for example, which is not terrible, I think. I think that's probably just as well.
We think that these are going to scale, by the way, to have hundreds of primitives in them and build really complex solid regions.
Mm-hmm.
Is that scaling? I mean, compared to like what exists right now, is the issue with scaling performance, or is it like the number of different types of primitives, or what?
It's the compute. I mean, it depends on what you want to do. Right now, we can't even visualize because discretization performance is not. Well, it's not just performance. It's a variety of things. But these ones, you can at least look at them. You know, even with hundreds of primitives.
And implicitly, when you have a CSG tree, there's a set of property you don't need to validate. That's one key thing, right? So based on that, like, is the object closed? Actually just know that, is it empty, right? Compared to Boolean region, where you actually need to do explicitude operation to know if the result is an empty set or not. Right? So there is those different computationally behind the scene. Right? Okay, the same for the visualization. So there is all those pre-assumption you can get from solid region.
Ideally, it'll be more performant eventually.
Yeah,
this is more. Yeah.
No, they'll all be more performant eventually.
By the way, people are asking on the live stream, why CSG and why not spell it out? Actually, I have a good reason for not spelling it out, which is these are actually two-dimensional things. And so if you say constructive solid geometry and they apply to parallelograms, it's kind of crazy.
Oh, but these are 2D solids.
What does that mean?
Perfectly fine.
They are ND, right?
Yeah, we do ND solids. These are 2D solids.
Oh, come on, Roger. Roger, that is disgustingly incomprehensible.
No, it's completely standard nomenclature.
I understand that, but that's an argument for using CSG, which people understand to be this kind of procedure. By the time you use solid, and you're referring to it as a two-dimensional thing.
Yeah.
Every elementary math person hears a solid. They think a pyramid, a cone. They do not think a triangle. A triangle is not a solid.
Of course it is.
Yes, but it is, but not in elementary math.
You know, elementary math is going to get updated.
Elementary math
think
will
since
not
the
get
ancient
updated
Greeks,
for hundreds of years.
Yeah, I think the Greeks probably used a similar word to refer to solid geometry, but I'm not sure.
Yes, I mean, it's been the same way for thousands of years, Roger, that people have made the distinction. I know in Euclid, there's a completely separate book about solid geometry.
Oh, the whole literature is completely confused between, it's like sometimes they say, they draw just a boundary for a triangle and they say it's,
okay. Roger, we're not solving this problem. This has been this way for thousands of years. We are not going to, we're not going to be able to solve this problem. And just by being persnickety, a whale is not a fish type thing, we're just going to confuse people. So I think that's an argument for calling it CSG, which is a kind of a brand name for this kind of approach. Unless we say,
no, I think we all agree, Stephen. We're all.
How does this relate to our synthetic geometry stuff? How does this relate to what we're doing there?
That's a language for talking about points and intersecting lines, right?
Well, and circles.
Oh, yeah, right.
And polygons. And polygons. So the difference here is that are you claiming, it has a notion of area, for example. The synthetic geometry system has a notion of area. So now I'm a little bit suspicious. I think we need to understand that relationship. Okay. I think that's going to be a separate discussion with different people, but I think we should do that so we don't produce something. But I think what we're understanding here is this should be CSG region, just like we can have mesh region, there's CSG region. Those are two kinds of implementations for regions, so to speak. Does that make sense?
Yeah.
Okay. And this whole question of regularization is a separate question which we have not properly addressed yet. And these different representations will at first kind of randomly choose to regularize or not. So, for example, in principle, region difference could have some kind of option that says, should you regularize or should you not, and could have a different target. It doesn't really need a different target because you can always say mesh region of the output, right?
Right.
Question. If I say CSG region, could CSG region eat anything other than primitives? Is there ever any output from region operations that can be cast into a CSG region?
Yes, but we won't. It's the level of complexity. So CSG region need to be built on top of, essentially it's a tree, right? So it's that nested tree of base primitive, right? We can extend it to each implicit region because you can represent the ball as an implicit region, but that will, defy the purpose of actually introducing solid region. CSG tree, CSG region.
Right. Okay. So look, we need to wrap in a moment here, but let me just look ahead here. What's this? Region convert. What was that before? Okay, hold on. We've got a whole bunch of new stuff here. All right. Yes. So create data structure these are data structure things. These are not top level functions.
They are top level functions, right?
No, just the same as the binary tree. So from the create data structure.
Right. That in that sense.
Yep, in that sense, yes.
So they're just string names in data structure, correct?
Right.
Correct. Yep.
And the very fact we're calling that CSG tree is good resonance with the CSG region.
Yes.
My gosh. Okay, so there's a whole bunch of new stuff here. Well, wonderful. It's wonderful there's new stuff. We're going to need at least another hour on this.
Right. I'll get a schedule.
I think.
Requested.
Okay, but But the things we're leaving hanging here are a little bit on this regularization of regions, right? Do we think anything is hanging for this version with respect to regularization of regions?
No.
Okay.
And just a note again on that, right? We had it since, I don't know, version 10 or such, right? There have never been an issue or confusion from a user point of view.
Oh, yes, there have. I've been confused about these questions of whether things are in or out of. I mean, whenever you're doing things which are elementary math, you get confused with this. I have been confused many times. You're thinking about fancy, super fancy math and super fancy, industrial
No,
scale.
actually, for me, the definition is documented, is simple. It's on the
simple if you
documentation.
think about fancy math. It's not simple if you don't. I mean, this business about, okay, in any case, that
right.
graph of a solid, oh my gosh. So that is the equivalent of a mesh connectivity graph for a CSG region. Is that correct? Solid region tree graph is, right? That's the equivalent of a mesh connectivity graph, but
no, it's the construction tree. If you look at the reference page,
so that
first tree to the left there, that's the tree.
Yes.
Which is a little bit analogous, like at least to the extent that it's like a mesh is just you take a bunch of points and lines and you sort of assemble them in some way, and this is you're taking these other bigger primitives and assembling them. But,
sure. So, I mean, it's like a giant union. The mesh is like
the mesh is a giant union, right? Where every node in the mesh is a union node. Right. Every node in the mesh connectivity graph is a unioning node.
Right.
All all the primitive you are using in solid region, in CSG region, there are just cells, if you look at it that way.
Right, but so the thing that you get out, oh boy, it's a graph? How is it a graph? Why don't you make it an actual tree? Because if you made an actual tree, you could label the nodes by the operations. And then you could actually have it be the case that that CSG region could eat one of those tree objects and produce the actual region. See what I'm saying? Did you get what I'm saying?
Honestly, based on the distinction,
it's a matter of flavor, right? I mean, I won't argue with that. Here we want to map it back to the graph framework. That's one thing. If you want to map it in the tree framework now, right? This is an expert. No, this is an expression, right?
No, but I think we should call it CSG region tree. And it should be a tree object.
The thing is, I mean, the distinction we made earlier, right, was that you use graphs. For example, there's no ordering information if the nodes aren't repeated or if it's nonsensical for the nodes to be repeated. And trees are more if you're representing an expression-like thing where there is ordering, the nodes can be repeated, etc. Yeah. It seems like this is a case. This is really just a held expression, and the order matters a lot, and the nodes are repeated. So.
But that's why we have
to be a graph, a tree.
Yes, but that's why we have expression tree. I mean, that my thought at the time. I mean,
no.
This object is an actual. You'll be a normal expression, right? You just need
which
to apply.
Object?
CSG tree will be a normal expert. It will be an expression in the language. So if you apply expression tree on it, you should actually get.
I know, but CSG tree is not in the language. This is part of data structure.
No, sorry, I mean CSG region.
No.
The CSG region.
It won't immediately convert. I mean,
it should convert.
No, but it won't.
No, but like the vertices won't be labeled right. They'll be, it won't be a clean tree.
Right. Whereas this, for example, if this was a tree with nodes that were labeled by union, et cetera, this would be very nice. And it will be, if you really want the graph out, you just say tree graph, and that will give you the pure graph where you've dropped what the node labels are.
Okay, I mean, I won't argue that it's a matter of flavor between a tree graph and a tree.
Right, I think it should be. Just because you built tree graph and other people built tree does not mean trees should be, cast into the outer darkness, so to speak.
Not at all. I mean, we made a full integration to the tree framework. To the graph
I know, okay. You support trees. Plant a tree, good, okay. But I think this should be a tree.
Okay, we'll do that.
Okay. I'm because I'm impatient. I just want to know roughly what's coming up here. Lovely. Tauruses. Okay. Oh, tube is now supported as a geometric region. About time. That's good. Oh boy. That's all complicated. Well, we'll discuss this. Oh my gosh, you really have 3D Voronoi now? Wow. How many times have people asked for 3D Voronoi?
We didn't think we would get it, to be honest. This was...
But we have it?
Well, do we?
Not yet. We are working on it.
Right.
It's coming.
This is one of those which
I thought the number of times this has been requested.
No, we would get it eventually, but we thought we would have to build a whole new framework. So this is more like, oh, maybe we found a way around. This is like, since you're a big soccer fan, Stephen, this is when you hit the, of course you are. I mean, you grew up in soccer country, right? So this is when you hit the goal post, when it hits like the goal post and goes in. This is, I don't know, it's one of those. Okay.
Okay. Well, let's hope that works. That will be wonderful because it has been, it's one of our top most requested algorithmic things.
So in the category of Voronoi mesh requests, does this also there's also always been the issue of whether the cells line up with the vertex IDs or like you know what I mean? Like the order of the points that you give that you put in and whether those align with the numbers of the cells you get out. Does that make sense?
Yes, we won't per se be able to do that because you need then to run a role sorting. So, but the plan was, I think Roger actually requested to add a notation to the Voronoi.
Yeah.
So you can recover the information.
We support general annotations for meshes. So we want to provide those annotations that allow you to do those alignments.
Sure. Okay. An annotation would be a good way to do that. I mean, but also, I mean, is there no reason not to just use the cell ID?
But well, in terms of complexity, you can always do that. But from the result, we need to resort again the whole thing to just before we give you an output. So, roughly speaking, is n log n complexity we are adding on the operation. So
well, that doesn't sound bad actually.
Well, depend on
if you're
the size,
adding,
right?
Like maybe for the theoretical complexity, but it's like I have to imagine. I mean, if you already can get the alignment, right? Because you can add it in annotation. I have to imagine the actual computation time of reordering the things would be absolutely infinitesimal compared to computing the actual mesh.
Not really. For the annotation, we actually keep track, right, through the whole process. So we actually have the information.
Right, but you could just keep track the whole time and at the end reorder them. I mean, I don't know. I mean, it just seems like it's a matter of calling part, which is generally pretty quick.
Well, we'll try to see what we can do. Can't guarantee that, but as long as we keep the complexity down. So.
All right, we've got lots of things to look at still. This is going to be at least another solid hour. And by solid, I don't mean... Okay, sounds good. Thanks a lot, guys. Thanks